everyone. This is Unit 4 review video to help you get ready for the final exam. I'm going to make a second video talking about the final exam. This one's going to focus exclusively on the Unit 4 material. So we'll just go section by section here. Hopefully me writing in a Word document isn't bad. And then I'll upload this Word document for you all to use. Or maybe I'll just if I can attach it to the YouTube videos, I'll do it there. Okay, so in section 4.1, we learned about everything probability. So let's see, let's start with the definition of probability here. Boy, can I spell it? Probably, haha. Okay, so probability is, it's a number, let's say that. So a number that measures likelihood of an event occurring. Well, let's change that. We should really say of a random event occurring. And it's measured as a percent, a decimal, or a fraction, provided each of those representations are a number between 0 and 1. And we associate some words with these numbers. For example, 0 means the event is impossible. So it can't occur, it won't happen. And 1 is the event is certain to happen. Boy, that is not how you spell certain. Let's try again here. And then this 0.5, it's equally likely to occur or not occur. So I'm just going to write here equally likely. And then anything less than 0.5 is unlikely to occur, and anything greater than 0.5 is likely to occur. Obviously, the closer we get to 100, the more likely it's going to happen, right? Noted in this is we can't have negative numbers or numbers greater than 1. If I were to write these numbers as percents, hopefully you know 1 would be 100%, 0.5 would be 50%, and 0, of course, would be 0%. As fractions, well, this is just 0, this would be 1/2, and then this would be any number over itself, 3/3, 5/5, whatever. So some of the questions I'm going to ask you, like what you saw in Alex, was like, hey, what of these numbers in the list could represent a probability or what couldn't? So, for example, 4 thirds could not be a probability because it's a number greater than 1. All right, so that's the basic concept of probability. What we then you need to have a basic understanding of what a probability experiment is. And that's just any random process that's repeatable. Our textbook says a process that leads to well-defined results. So I'm just going to say a repeatable process. Well, let's be careful here. It's a random repeatable process. And this definition might exclude some things that we consider. Is that how you spell repeatable? We're going to go with it. So what this could exclude is the college, like Jackson College, tries to predict the number of students that we're going to have in upcoming semesters to plan how many classes we should run, how many sections of each class, and etc. And while that is not really random, it's definitely a repeatable process because each year we have a new set of students come into Jackson College, or so that fits under. We use a probability experiment definition on that, even though this kind of makes that seem like it isn't. And then each experiment has what's called outcomes, and those outcomes, it's the result of a single trial. So like one semester at Jackson College. The more common examples we use here is, say, drawing a card randomly, or drawing a card from a shuffled deck of playing cards, or rolling a pair of dice, or picking lottery numbers, that kind of thing. So from that, we get what's called the sample space. And this is important. You need to be able to define this. I'm sure you saw this in your Alex homework. And this is the list of all possible outcomes in a sample of a sample space. Of a probability experiment. So list of all possible outcomes of a probability experiment. So you need to be able to define the sample space. That's pretty important. And well, really the most important thing from this is knowing how many outcomes are in the sample space. So for example, let's say our outcome from the notes is rolling a 6-sided die. Now let's say rolling a 20-sided die for you D&D and Magic the Gathering fans. So the sample space, I'll just do SS, we often list it with these little brackets, would be all the possible numbers, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 20. So there are 20 possible outcomes in this. And then an event would be, what's the probability of rolling a 4? We often use this notation. And I'll just write in words here, rolling a 4. And then here comes the next thing you need to know. How do we calculate a probability? It's the number of events, or number of outcomes in the event. Here, there's only 1 4 in our sample space, divided by how many outcomes there are in the sample space. So this is an example. Let's put a general definition here. Probability of an event is equal to the number of outcomes in the event divided by the number of outcomes in the sample space. That fraction. Okay. Boy, was there anything else from this section? No, that's basically all we did for probability. We just wanted a real basic understanding. We then skipped the last half of 4.1 and 4.2 and 4.3, and we moved on to statistics. So let's see if we can make that happen. Okay, so these are just going to be backwards, whatever. All right, so in 4.4, there's a bunch of stuff we learned there. This is where we encountered the definitions of a population versus a sample. So you need to clearly know what is a population. And in the context of statistics, the population is all individuals in a study. And then a sample is a subset of the population. And the whole point here is it's really difficult often to collect data from the population. So instead, we take a smaller sample. We take a sample of the population, which is a smaller amount of individuals, and we collect data on that sample, and then we make an inference from the sample about the population. For example, in the political world, when we're trying to predict which candidate is going to win an election, we call 400 random likely voters in the U.S., or if it's a federal, like a Senate election, well, really it'd just be the president, because the states would elect the senators and the House representatives. So let's go with that example. Say we want to know who's going to be the next senator in Michigan. Is it going to be Gary Peters or someone running against him? I don't think he's up for election in the next round, but whatever. So we ask 400 likely voters in Michigan, who are you going to vote for? What's important is that this sample represents the population. So when we collect the 400 people in the sample, they need to be from all kinds of different areas in Michigan, the UP, urban, suburban, etc. And we ask them who they're going to vote for, and then we take the percentage of people that are voting for one candidate from that sample and project that onto the population and say all voters in Michigan are going to vote similar to the way those 400 voted, and then that's what gets reported and tracked. Okay, so we then looked at how can we create good samples, good representative samples, and there were 4 types of sampling methods that we talked about, and in all 4 types you needed notions of randomness. So there was just the basic random sample, and that is where each individual in the population is equally likely to be picked, and some sort of random process is employed to select the people, like what I showed in Project 4, where we used a random number generator and randomly selected a number between all the possible outcomes. The next one that's similar to this is systematic. Our textbook kind of leaves out some of the details on this, and I glossed over it myself. You number the population, you randomly select a starting point, and then you select every kth individual. Oh boy, I forgot the word select. There's also a process of how to determine what number to use for K that helps make sure you get a good representative sample. We didn't talk about that in this class. If you take our statistics course 133, we do give a better description of how that happens. All right, and then there were 2 very similar methods. There's the stratified method, and this is where you group the population by characteristic. And randomly select in individuals from each group. So you're selecting from all of those groupings. Whereas cluster, you do the same thing. You group by characteristic. I'm going to leave out the population. And then you randomly select in groups and record all the data from all the subjects in the group. So you randomly select in groups and collect data on all individuals in the group. So like the Alex homework on the exam, questions I might ask related to this would be to give you a scenario, a sampling scenario, and say which type of sampling has occurred in this scenario. And then 2 more things from 4.4. That would be, well, actually, there's 3 more things. So we have the definition of categorical data, or as the language we would use in our stats class, okay, qualitative data. And this is data that cannot have meaningful, this is a terrible way to say this, but whatever. Calculations done on it. Okay, so we can't calculate the mean of categorical data. We can't calculate the median. The only thing we can really do is figure out a mode. And often what we do with categorical data is we transform it into quantitative data, which is the next one. Hey, there's the name of our class. And this is just numerical data. But we need to be a little more precise. Numerical data for which meaningful calculations can be done. So we can calculate a mean, a median, a mode. An example of numerical data that's categorical would be your social security number. That's just your name as the government, in terms of the government. Okay, and so then what we did with that mess is, just going to get a bunch more pages here on that, is we then created grouped frequency distributions and categorical frequency distributions. So you need to be able to read those and understand the kind of information they tell you. So let's see, we need, what's up with the categorical frequency distribution? And a grouped frequency distribution. And what we did with the group frequency distribution is we figured out how to find classes and the class width and how to put our data into those classes. Let me just reference you to the page 357 where this comes from. And we created, and then from this we also had a stem and leaf plot. These were just ways to organize and represent data. Make sure you know how to read a stem and leaf plot. If you're provided a key, there's a good chance maybe I took the number of hours students in my online class, which is most of the ones of you all that are watching these videos. I took the hours you spent logged into Alex and made a stem and leaf plot of that, and then ask you a bunch of questions on that. Okay, that's 4.4. 4.5 were measures of average. Also known as central tendency, or the middle. There are 4 that you need to be able to, quotes, calculate: the mean, the median, the mode, the mid-range. Desmos will do these 2 without a formula. The mode, it's the most frequent, and the mid-range is the maximum plus the minimum divided by 2. So make sure you know how to find those. And then from this, say, what do these tell you about the data? And then which is the best one to use? Depends on the data set. To answer this question, you need to know what an outlier is. So these are data values far from the other data values. That's essentially the definition we've given you. There's pretty sophisticated statistical tests to determine precisely whether or not something is an outlier. I've done a couple of my grad classes. It was last semester, actually. We are not concerned with doing that at this point, just the basic idea. Remember, if there's outliers in your data set, you want to use the median. If there's not, the mean is certainly appropriate measure of average. 4.6 then was measures of variation, also known as spread. For this course, we looked only at 3. So you need to know how to calculate the range, the standard deviation, and the coefficient of variation. Boy, I'm going to have to look up how to spell that coefficient. I always spell that one wrong, I feel like. And same questions above, which is best? What did they tell you? We also, by the way, noted that we called this C subscript V. And then I'll put this as a side. We need to know the sample symbols and the population symbols for each of these measures. And there's only two that actually have unique measures for them. The mean is X bar, the population mean is mu, and for the standard deviation, the sample is S, and the population is sigma. And the standard deviation has different calculations depending upon whether we're working with a population or a sample. So make sure you know how to tell whether your data set is a sample so you can determine which function to use in Desmos. So in Desmos, stdev is for the sample, and stdevp is for the population. For whatever reason, ALEK's homework assumes all the data sets are populations, so they always do the standard deviation for the population calculation. Typically, however, your data set is not from a population unless you know that all the individuals of the study are in there. So, for example, if we wanted to know the average height of American presidents, we know how many presidents there were, 46, I want to say. Help me out if I'm wrong there. At any rate, and we probably have that data for all of them. And it would be pretty easy to calculate that population mean height or that population standard deviation height. But if we wanted to know, for instance, the mean height of all American males, that's a really difficult population to gather. You'd have to measure all males, and how likely is that actually to happen? And you know, there's those folks off the grid in the backwoods of every state that you're never going to get to. Okay, that is 4.6, and then finally 4.7. We talked about the normal distribution, and there's really just two things to go with that. In your reference sheets, as you're taking the final exam, you're going to want to have the empirical rule spelled out. And essentially, you want to fill in, come on now, you want to fill this in with all these lines and their percentages. I'll put the page number on there. Just a little heads up, I probably said it in the videos. If you're taking our stats class, 133, they use slightly different percentages in there. Neither textbook author is wrong. They're just slightly different, so just be aware of that. So there's that, and then you need to know how to calculate a z-score. And that's just the data value, easy there, killer, minus the mean divided by the standard deviation. It's like what you're doing in the notes or in the project. And then you need to interpret this. So remember, a z-score is the number of standard deviations a data value is away from the mean. That's kind of a confusing definition. Let me try to make it better. In other words, we're calculating the distance a particular data value is from the mean, and the units of measurements are standard deviations. So, for example, if we're talking about the mean heights of males in America, and say a particular male, let's do me, say my z-score is 0.32, that would mean this male is 0.32 standard deviations above the mean. And the practical interpretation of that is this particular male is just slightly taller than the average male. If we had, say, a z-score of like -4, it would be this male is 4 standard deviations below the mean. Which means this particular male is quite short relative to all other males. Like really, really short, actually. A -4 z-score is really unheard of. If you think up here, in terms of z-scores, -3 is here, and 0.1% of the data values are less than 3 standard deviations away from the mean. So if we're 4 standard deviations away from the mean, that is just crazy unlikely. Oh, let me remember one other really important concept that came from this normal curve. That area under the normal curve is equal to the percent, which is equal to the probability of randomly selecting a data value. So that you were to make that connection and figure out how many of a sample might fall within a given range of values. There's a bunch of Alex homework specifically related to this normal curve, and your project, the Milk Data Project task 3 works on that. All right, so this is the Unit 4 review. If you go back and look at all 4 reviews, you would have a pretty good understanding of what's going to happen on the final exam. But I will make another video specifically talking about the final exam and what to expect.